Hi, this is Ana Doblas with a video of ECE 513 course. In this video, we will introduce the different type of mirrors, including the spherical mirror. We're gonna talk about their features and the number of focuses, and at the end, we're gonna show how to determine the location of an image through a mirror in both ways, like qualitative using ray tracing and quantitative applying the imaging equation. So the first mirror is the planar mirror. So assume that you have a point source P1, and from the point source you emit rays at different angles. And because we need to obey the reflection law, then the incident angle for every of these rays, the incident angle and reflection angle is going to be the same. So remember, we are always defining the angles through the normal, and that means that those angles are exactly the same. So as you can see, the reflected angles, they don't converge on the left side of the mirror, but those rays look like they come from a virtual point source P2 that is located behind the mirror. The second type of mirror is the paraboloidal mirror. So in the paraboloidal mirror, the feature is that any parallel ray converges to a focal point. So the distance between the vertex of the mirror and the focal point is called the focal length. And those mirrors are really important either to create parallel beams or to focus point sources. Elliptical mirrors are those that they're gonna be defined by two focal points, P1 and P2. The whole idea is that any ray emerging from P1 is gonna converge in P2. And the important thing is that the optical path length of the rays is the same. So all the rays have the same distance to travel. They're gonna take the same amount of time. Spherical mirrors are kind of like the more general mirrors. So spherical mirrors, they're gonna reflect parallel rays, but every parallel ray is gonna be reflected in a different point within the optical axis, so they don't gonna converge to the same focus. When we are thinking about spherical mirror, we need to take care about the surface, where it's kind of like going if we have convex or concave mirrors, because depending on the mirrors, we always gonna have like the values of the radius is gonna change. It can be positive in convex or negative in concave. So spherical mirrors, even though we say that in general parallel rays are gonna converge in different points within its axis, for those rays that they travel close enough to its axis, they always gonna focus on the focal point, and we're gonna define the focal length as half of the radius of the curvature of the spherical mirror. So the rays that they travel close enough to the mirror axis, those are paraxial rays, and in paraxial rays we have that the sine of the angle when they meet is approximating the angle. And for that particular case, our spherical mirror has two properties. So that means that we have the focusing property as the paraboloidal mirror, meaning that any parallel beam meeting the spherical mirror is gonna converge to its focus. But we also have the property of the imaging property of the elliptical mirrors. So the imaging property, what it's telling us is that any ray emerging from P1 is gonna go the image through P2. And what we need to take care here is not only taking care of the radius, if it's convex or concave, but we also need to take care of the angles. So we're gonna define positive angles when the light kind of travels from left to left. So it's kind of like a ray traveling upward, but then theta 2 is going to be negative. So when we are thinking about the imaging equation, what we need to know is typically we know the location of your object, or you know the location of your image. You need to know the focal length of or the radius of your spherical mirror, and you're gonna be able to estimate either your object or image location based on the focal length. So when we are having mirrors, something that is gonna be different than lenses is that the left side on the mirror, this is my real space, but because the mirror reflects light, right? Everything located behind the mirror, that's gonna be my virtual. So virtual object, virtual images, they're gonna have negative values of my distances. And then real objects or real images, they're gonna have positive values of it. In a general case, we can assume that we have a parallel beam. So when we have a parallel beam, means that our ray is placed at infinity. So the one is infinity. So let's assume that this is gonna be my ray coming through the parallel. And now in that particular case, the ray is gonna focus on the focal length. And that's where I'm assuming that this, so 1 over infinity, that's gonna be equal to 0. So just telling me that the image of a parallel beam becomes to my focal. It's equal to the focal. So D2 is my focal. So about the qualitative estimation of the rays. So we always need to draw 3 rays, although 2 rays are enough to estimate the image is gonna form when the 2 rays or the 3 rays meet. So let's assume that we have an object. I'm assuming a concave mirror, right? So the first ray, the red ray, is the one that goes parallel through it. From the height of the object has a parallel beam, and when it meets the mirror, because it's parallel, you know that it needs to meet the focal point. And remember, this is my real space and this is my virtual space, right? So this is one of the rays. The second ray is the one that passes through the center of the spherical mirror without distortion. And our third ray is the one that goes from the object to the focal point until it meets the mirror, and when it meets the mirror, it cannot exit in a parallel. And this is the point when we have the 3 rays converge. So if we draw an arrow through the optical axis to the point, we're gonna see that the height of the arrow is related with the size, the height of the image. So the image is smaller than the object, and because the arrow is pointing down, that means that it's inverted, and because the point of conversion is on the left side of the mirror, then the image is real. We can do exactly the same tracing from a convex mirror. The only difference between convex and concave is where the focal length is located. So in concave, the focal length is placed on the left side of the mirror, and in convex, it's on the right side. So for a convex mirror, again, the red ray, we have parallel beam, and then we are meeting the focal point. We have a ray going through the center of the mirror without changing the angle, and then we have a ray going to the focus, and when it meets the mirror, it gets parallel. And what we can see here is that my object is straight, so it's erect, it's virtual, because it's placed on the right side of the mirror, and the arrow height is smaller, so the image is smaller than the object. Alright, so in summary, we have talked about 4 different mirrors. The paraboloidal mirror is the one that it has a single focus, so all the parallel rays converges to its focal point. The elliptical mirrors have two focus points. So this is the imaging property. Rays emitting from one focus is gonna meet the other. Spherical mirrors, in general, you cannot define any focal point because parallel rays converges in different points within its axis. But if we are under paraxial approximation, we're gonna have the focusing property of the paraboloidal, and then we're gonna have the imaging property of the elliptical. And we can use the imaging equation to estimate quantitatively estimate the location of the image or the object given the object and the focal length of the mirror. Thank you.